Hello everyone. So we started unit number 4 and in binary system we discussed 4 binary reactions: eutectic, eutectoid, peritectic and isomorphous. So lead and tin for isomorphous system, copper and nickel system was already discussed with you, and we discussed one numerical also. So I hope there is no problems in at all. Now we are going to discuss eutectic system today. In eutectic system, as mentioned in the syllabus also, we will be having lead and tin system. So this is the phase diagram for lead and tin system, and right now we are seeing one general diagram as discussed earlier also. So this capital A indicates this is metal 1, capital B indicates it's metal 2, this TA indicates it's the melting point of pure matter here, and here TB indicates it's the melting point of pure metal B. Now as soon as we mix or make an alloy of this system, the slope tells us that any alloy which will be forming will be always having melting point less than it. Suppose we consider from the perspective of A. Let us consider A is having melting point of 500 degrees Celsius, and this 10 indicates there is a 10% indication of metal B into it. So at this composition it's 90% of A and 10% of B. Now pure melting point was 500 degrees Celsius. As soon as we are adding 10% of metal B at this point, it indicates the melting point is less now, and this trend continues, and see how it going to decrease. Now it makes a slope. Similarly, take from the B's perspective. From B's perspective, B's melting point, let us consider it is 1000 degrees Celsius. So at this point, which indicates 90 here, it means it is 90% it is B and 10% is A here. So again, if it is 1000 degree Celsius for pure melting point, on addition of 10% of A at this point indicates the melting point is lesser now, and again this same trend continues to follow in B case also. Now both these slopes meet at a one point which is indicated by small e here. So small e indicates equilibrium point or invariant point, or the topic says eutectic point. So this indicates, as our reactions follows, that it if you are heating that alloy it will form into liquid, if you cool that alloy it will form into two different solids, indicating it is two different phases. So the point E has got the significance that at this particular temperature, if you heat it just by 1 degree Celsius it will be complete liquid. If you cool it below this temperature even by 1 degree Celsius it will form two different solids here. Okay, so this is the significance of point E here. For any alloy, this is that point where this change of phases just takes by minimum temperature. Slightly increased temperature it will be different phase, slightly decreased temperature it will be different phase. In this case, slightly increase it will complete melt, slightly decrease it will be combination of phase A and phase B here. So we already discussed about invariant point or eutectic point, and see in this diagram it is shown it is 50-50 here. None of the case, it may be other composition also. For the general cases it has shown it is 50% of A here, 50% of B here, but it actually depends upon the slope only. So if the slope is drastic in any case, it will be lesser also. It can be 60-40 also. Now see, go to the definition. Eutectic temperature, it's the minimum temperature at which solidification occurs. Remember, if you increase the temperature by 1 degree Celsius, it will be completely melt. So next one is, so see the phase rule equation, it's modified right now. It's P plus F equals to C plus 2. It was earlier for the isomorphous system, but for for the unary system, but in all binary systems it will be indicated by plus 1. So plus 1 indicates for temperature. Here we are removing out the pressure variable right now, so it will be one variable which is temperature, and the other axis will be using as composition, not to be mentioned as 2 here. So this is the Gibbs phase rule equation, and yes, it has founded the degrees of freedom at point number E. So at point number 3, three phases simultaneously coexist, that is liquid phase and two solid phases. So that's why it is number of phases equals to 3, and number of components, since it is a binary system, it indicates 2. Calculation will give you F equals to 0, means you cannot change the composition and temperature if you want to find out point number E. You are having 0 degree of freedom here. Now, this is the equilibrium diagram or the phase diagram for copper and silver, but we'll be first discussing lead and tin system. So, lead and tin system indicates here this is lead, so we are having it metal A. This is tin, we are having it metal B. The topmost point, it indicates the melting point, which is 327 degrees Celsius for lead and 232 degrees Celsius, which is for tin. So it is pure melting points. And see here it is showing you the eutectic point also. See the slope is going down here, slope is going down from 230 towards this point also. So it is exactly 61.9 and 183 degrees Celsius. Remember we calculated degrees of freedom, so it comes out to be 0. So I was talking about this variable only, which says the composition, which is 61.9 and temperature 183 degrees Celsius. You cannot change out this point. For lead and tin system this remains fixed. So it is 61.9, so you just increase by 1, so you just increase by 1 degree Celsius, means 184 or 185 something, you will be observing it as a liquid. If you decrease it by a few degrees, you will be observing it as a complete solid. Alpha will be the symbol used for metal A, which is lead, and beta will be the symbol used for metal B. So alpha and beta indicates it's a solid phases, and liquid will be indicating with capital L, like it is shown here. Okay. Now this also shows one more information, that at room temperature your curve is not starting at 0 only, because you cannot dissolve any quantity of tin into this portion, which is lead. You can only do so if you say slightly increase beyond 50 degrees Celsius. At this point some part of tin can be dissolved into lead part now. So this is the common example also. As you increase temperature, more sugar can be dissolved into the solution. So same way here also in this lead and tin system, lead can allow the possibility of dissolving tin only above 50 degrees Celsius say, and as soon as you are increasing temperature, more amount of other concentrations, and it goes up to 18.3%. So you consider it, since it is on the lead side, more percentage will be for lead, and this 18.3% actually indicates for tin. So only this much maximum percentage can go up to 183 degrees Celsius. Let us make it easy. If you are having an alloy system of 100 grams which contains some quantity of lead and some quantity of tin, so this 18.3 indicates that out of 100 grams at 183 degrees Celsius, only 18.3 grams of tin can be maximum dissolved. And if you further increase the temperature, solubility again decreases. Similarly, if someone thinks in tin, if I want to add lead, so now the perspective is you want to have a solution of tin, and someone thinks he wants to add lead into it. So add say 50 also, 100 also. So like about it is following same degree Celsius scale only. It is again nearby 50 degrees Celsius. You start getting addition of lead into tin, but the trend shows you can have maximum quantity about 2%. Now for which 2%? See, 97.8 is indicated towards tin side. So this is the number for tin. This complete scale is with the reference of tin only. So at this point, which is at 183 degrees Celsius, you can have 97.8, or we call it 98%. So 98% will be tin, and only 2% you will be able to add lead into it. So this also tells you that metal B, which is tin, will allow just 2% of lead into it. So it's not possible to make a solution of tin and lead. It is possible to make solution of lead and tin. How can we justify this? We can say that the atomic radii of tin is very small, which will not allow the bigger atomic radii of lead into it. However, the case in lead, the atomic radii are very big as compared to tin, and small tin atomic radii can be easily accommodated into lead ones. Okay. So let's have one numerical problem also. So see, it's giving you for a 40% tin and 60% lead at 150 degrees Celsius. So though the questioner will always giving you two variables, one will be the composition and one will be the temperature. So it is specifying you 60% of lead. So you are having 100% lead here. So it is 100% lead, 80%, sorry, 100% lead, 90% lead, 80% lead, 70% lead and 60% lead here. Or go with the case of tin also, you are having 100% tin, 90% tin, 80% tin, 70% tin, 60% tin, 50% tin and 40% tin. So whatever the case is, you will obtain this point, and at 150 degrees Celsius you will mark one point here. So you marked one point which is indicated by B here. Now it is talking you what are the phases present. So phases present, as you are below 183 degrees Celsius, you are below eutectic point, you observe there are two phases. So it will be alpha phase and beta phase. Alpha phase indicates lead and beta phase indicates tin, both in solid states. Now what is the composition of this phase? Now we remember that lever rule, it says if anyone is asking you about the composition, so you first step is to make a tie line. So tie line is a horizontal line which connects two sides of solidus. So you are extending towards this side and extending towards this side also. Now this will be point number 1, this will be point number 2 and this will be point number 3. Again I am telling you the point number B is actually given by the numerical statement, which is at 40% in and 150 degrees Celsius. You indicated point number 2. After this we are drawing left hand side and this right hand side, we are connecting these two and we stopped by these two solidus lines here and here. Mark it point number 1, mark it point number 3. So we are having 1, 2, 3. Next step is to apply lever rule here. So application of lever rule will be, you will be having it in the terms of composition. Now draw perpendiculars here and draw perpendiculars. You will be making it, let us say we'll be writing in terms of tin. So this is approximately 98%, this is approximately, or it's given in the statement only, this is 40% and this is slightly more than 10, so we'll be writing it 11%. So it is 11% in, this is 40% in and this is 98% tin. We are writing in the terms of tin now. Next step is to write percentage of alpha and percentage of beta, which is lead and tin. Apply lever rule here and you will be able to calculate the required quantities. If any queries in this numerical, you can ask again. Thanks.